Okay, so this is the last video for chapter 3, and it's on proportionality and density. Here's our goals. There's a few of them. We want to be able to write a mathematical expression indicating that one quantity is directly proportional to another, use a proportionality constant to convert a proportionality to an equation. Given the values of two quantities that are directly proportional to each other, calculate the proportionality constant, including its units, and write the defining equation for proportionality constant and identify units in which it might be expressed. And then finally, given two of the following for a sample of a pure substance, calculate the third: mass, volume, and density. Okay, so a direct proportionality exists between two quantities when they increase or decrease at the same rate. And if a graph of two related measurements is a straight line that passes through the origin, the measured quantities are directly proportional to each other. So for example, if I try to draw this, whoa, hello, didn't mean to do that. Okay, it looks something like this. Let's say that's quantity 1, and that's Q2, right? There's a straight line that's going through the origin, okay? So we can describe direct proportionalities between measured quantities using per expressions. So direct proportionalities between measured quantities yield two conversion factors between the quantities. So given either quantity in direct proportion and the conversion factor between the quantities, we can calculate the other quantity using dimensional analysis, okay? So that's the goal here. So the mass and volume of any pure substance at a given temperature is directly proportional, all right? And a proportionality is changed into an equation by asserting a multiplier called the proportionality constant. So for example, let D be that proportionality constant. We could say that mass is equal to some proportionality constant times volume, all right? So solving for the proportionality constant yields the defining equation for a physical property of a pure substance called density. So in other words, if we have mass is equal to this proportionality constant times volume, if we divide both sides by the volume, the unit of volume cancels on this side, okay? And we're left with mass divided by volume is equal to density, okay? So this is our equation for density. The proportionality constant here is what we will define as density. Okay, so let's do an example together. No, I lied. Here's a table of the densities of some common substances, just for reference, that we can have them. And just, just know a few of these densities and kind of gives you an idea if you were curious. So moving on from there now, we're going to use one of these densities in the following example. It's not letting me go. There we go. So in the first example, it says, what is the volume in centimeters cubed of a 15-gram piece of silver? The density of silver is 10.5 grams per centimeter cubed. Well, again, we're going to use dimensional analysis. So we're given 15 grams. We want volume, centimeters cubed. Our per expression is going to be the density. So this is going to be, I'm actually going to express it this way. There's 1 centimeter cubed for 10.5 grams. And you'll see why I'm doing that in a second. And the path, we're going to go 15 grams to centimeters cubed. All right, so let's write that out as an algebraic expression, or as an equation, I should say, using dimensional analysis. And this has two sig figs. So I'm just going to say that right off the bat. So our answer can only have two significant figures, okay? So let's do that. 15 grams times, for every 10.5 grams, there's 1 centimeter cubed. And I flipped that per expression for this reason so that the units of grams could cancel out, okay? So if I wrote it the other way, the units wouldn't cancel out. So remember, that's a good way to check to see if you did these problems right. So when I do this, I get 1.428 centimeters cubed, okay? However, this doesn't have the proper amount of significant figures, so I need to round it to 1.4 centimeters cubed, okay? 2 sig figs. All right, let's continue on here. The mass of a 12.0 centimeter cube piece of magnesium is 20.9 grams. Find the density of magnesium in grams per centimeter cubed. Well, there's a few different ways you can do this, but the easiest way probably is not to use dimensional analysis. It's just to divide the two. I guess this is the only way you could do it now that I'm thinking about it. But just use the equation for density, which is mass divided by volume. Plug that in your calculator, 20.9 grams divided by 12.0 centimeters cubed. Okay. Let's write this, or calculate this, excuse me. Okay, and I get 1.7416 grams per centimeters cubed. That's the density that I calculate here. Okay, and the problem is what? Well, this has the incorrect amount of significant figures. If we look back here, that has 3 significant figures, this has 3. So this needs to be rounded to 3 significant figures, which will be 1.74 grams per centimeter cubed. Okay, so I believe that's it. It is for chapter 3. Congratulations, we did it. And next time we'll be learning about, I believe, gases in chapter 4. I think that's right. So I'll see you there.